Right, this looks like everyone, so I'll go ahead and get started for today. So I'll do a bit of a recap of what we did last time, and then sort of go over what we're going to do this time. So last time, if you remember, we had like, I don't know, 100-something lines of really ugly OpenGL code in our main function here. And it did what these two lines are doing effectively. It created a vertex array, took some vertex data, put that in a vertex buffer, described that vertex buffer, then created an index buffer to match it. And then, of course, in our game loop down here, we're drawing all of it. So we did a really good job of condensing all of that and making it very clean. We're going to do, the first thing we're going to do real quick is just add a simple little class that contains both a vertex array and an index buffer. Because for our uses, they're almost always going to be packaged together. And they're sort of designed that way already. Because if you remember, our index buffer constructor takes in a vertex array and creates as many indices as necessary to draw that whole array. So they're pretty much linked by that, but we'll go ahead and just make a single object to hold all of it for us. Once we do that, we are going to do another quick class, which is the renderer, which is going to help us clean up some of this stuff. Remember, our goal with like abstracting all of this out into a library is to make it so that the user doesn't have to write any of these GL functions. We don't want them to have to use any OpenGL code themselves. They should be able to do everything they want through our classes. So the renderer will handle clearing, drawing stuff, and swapping buffers and everything. And eventually it'll keep track of some more stuff. And then once we do that, we are going to write the shader class, which is going to take this, 50-something lines of code here, and put it all in one file. And it will also allow us to move this sort of hard-coded shader source code out into a separate file, which will be a lot nicer. Real quick before we start doing that, something I said last time that was maybe kind of confusing is when I was talking about the keyword virtual. So I'll just sort of clarify. When you have a virtual method, let me find that. Like if you have a virtual method here, when you like redefine that or override that in a child class, it is truly overriding it. The functionality of the original method in the base class, whatever that is, will not be called. You can still access it, but it won't be called by default. However, when you have a virtual constructor or destructor, like this buffer destructor here is marked as virtual, this is still called by child classes who, in quotes, override the destructor. So see, we have this virtual buffer destructor here, and then in our index buffer, we sort of define a new constructor. And if this buffer constructor wasn't marked as virtual, what would happen is when our index buffer is destroyed, all it would do is this printf statement, which clearly is not right because we've created a buffer up here with the constructor and we need to delete it. And so marking this destructor, this buffer destructor as virtual means that this index buffer code will run first, and then once it's done, immediately after that, the buffer destructor code will run. So it's sort of the constructor and destructors are flipped, where destructors, the base class is ultimately called first, the code in the base class's constructor is run first, and the destructor, the code in the base class is run last. Which makes sense and is good, because if you have a base class that has some functionality and then a child class that adds some more functionality on top of that, if you need to do any sort of cleanup for that stuff in the child class, that should be done before the base class destructor is called. So it makes sense, and it's just something you'll get used to as you write. But yeah, I just wanted to clarify that because I didn't explain it very well last time. Okay. So let's get right into it. I'll delete those and then come over here.
Can you increase the font size, please?
Oh, yes, I forgot to do that. There we go. All right. Let's create a new header file here. Render object. And this is just going to take a vertex array and an index buffer and store them in a single place. So I'll go ahead and include this in my all.h. Now, I don't know if I explain this. If you haven't used C or C++, it might be confusing. But if you like include stuff before you include another file, like everything included above this render object file will be accessible in the render object file, which I don't know, is kind of weird if you're coming from Java and like everything is automatic. But yeah, that's why I do it sort of in this order, where all the dependencies of a class are included before that class. And also now I don't have to include vertex array or index buffer in here, which is kind of nice. Okay, so we have our render object class. Let's get the variables down first. So we're going to have a vertex array and an index buffer. And that's it. So all our constructor is going to be is we could have it take in like a vertex array and an index buffer that are already created, but that's kind of messy. It's like not as nice for the user having to define this stuff before creating the object. And plus, that would mean we would have to go back to our vertex array class and define one of these copy and move constructors, which we just want to avoid because there's no reason. So instead, we're going to do, well, I guess it's like a pass-through constructor, I guess, where we're just going to take in all the data necessary to create the variables and then create them ourselves, which is just a little cleaner. So there's our vertex array. We want to make sure that we create that first, because remember our index buffer requires a vertex array in its constructor. So we'll do just like that. We have the number of elements in the vertex data, and then the sort of initializer list containing the groups of elements. And of course here we will delete those copy and move constructors to avoid as many obnoxious issues as possible. We don't need a destructor for this class because we have nothing to clean up, no pointers to delete. I guess if we wanted, we could have a destructor that says like this render object has been destroyed, but the compiler will sort of insert I guess a way to think about it is the compiler will insert a default destructor here that basically just destroys these objects, which is kind of what's happening. It's like when this object is destroyed, everything it contains is destroyed as well because it goes out of scope, so this stuff goes out of scope. So basically we'll already get those messages saying like deleted this vertex array and this index buffer, so we don't need to add anything else. Now for our bind method, notice that this isn't a GL object. It doesn't inherit from that because it's not really like an OpenGL structure. It's just sort of a convenience thing to combine two. So this bind method is not going to be override because there's nothing to override. But all we're going to do in here is bind both of our variables. Bind the vertex array and then the index buffer. Just save us some writing. And then something we're going to use a bit later on. It's nice to have the number of indices in our index buffer. So we'll just do sort of another like wrapper function here, similar to what our constructor is, that just returns the result of this other method directly. Okay, yeah, so that's very simple. That's all it is. So if I go back to the main file here, I can comment out these two lines and just write one line. A GFX render object, passing it the same parameters as I had passed to the vertex array. There we go.
Just had a quick question.
Sure.
So what was in the get index count again for the render object.h?
We're just returning the getCount method of our index buffer.
Oh, gotcha. Thanks. I just wanted
Yeah.
to make sure I had that.
Okay, and now we can also replace these two lines with just our render object.bind. What did I call it, actually? Oh, I didn't call it anything. So render object RO. Then we have the number of elements, the vertex data, and the description there. And then down here, we can replace that va.bind and ibo.bind with just ro.bind. And here's where we're going to use that getIndexCount method, which is nice because instead of like having to do like ro.getIndexBuffer.getCount, which is just a lot of typing, we can just do .getIndexCount like that. And when I run, it should be exactly the same thing. Perfect. No changes, just a small convenience for us. Okay, so now we're going to do another pretty small class that we'll unfortunately have to come back to quite a bit and modify. I've tried to write this like structure everything in a way that I've minimized backtracking, but in certain cases that's just not possible, and this is one of them. Because our render is going to handle drawing everything. So right now we'll just start out with like I said, like this clear function, this draw function, and the render stuff, swapping the buffers here. But eventually it'll also handle shaders and textures. So we're going to have to come back to this. I'll go ahead and include it in my all.h, renderer.h. Oh, I spelled it wrong. It's not render. Renderer. There we go. But for now, super simple. We don't even need a constructor or anything. We just need a single method. Well, we'll do three methods. We'll do clear, which we'll just call GL clear on that GL color buffer bit. And then we will do draw, which will take in one of our new render objects, by reference, of course, and then just bind that reference, and then do the same call we have in our main loop right now, which is GL draw elements. The mode is GL triangles. We want the index count. Type is unsigned int, and we have a bound buffer, so we don't need anything there. I'm not sure why this is yelling at me though. There we go. Yeah, sometimes Visual Studio is like slow to catch up when you create new files or open files, like the syntax highlighting is all off. So that's our draw method, and then we'll do one last method here called render. And this is just going to do these two calls down here at the bottom. The swap buffers, so displaying everything to the screen, and polling events. But if you notice, we do actually need to pass this a parameter because the glfw swap buffers method needs a window pointer. And our render is not going to store a window pointer. We are going to be adding a lot to it, and it does do kind of a lot of stuff, but we're still going to minimize it as much as possible. So we'll just take in a const OpenGL instance reference called GL, and then do swap buffers on GL.window, and then poll events, which we'll get to eventually. Just getting input events and stuff from the keyboard and mouse, all that. Okay, so now we have a renderer. And even though we don't have like a constructor for it yet, because it doesn't store any data, the compiler will generate one for us. So we can just define a variable like this, gfx render, and then we can start replacing this stuff with render.clear. And here we can do render.draw RO. And once we create the shader class, we'll also move this GL use program stuff into the renderer, so that the draw step is truly just one method call. And then down here, do render.render. Of course, with our OpenGL instance. Okay, so that's also simple, just a bit of housekeeping, just moving stuff out of here, making it as easy as possible for the user. So if I run this once again, hopefully no build errors, and should give us the exact same thing. Perfect. Okay, so now we're going to get into the interesting part of what we're doing today, which is all of this shader stuff. So this is a big class, and I don't know, it might take the rest of this session to fully write it. But I don't know, maybe not. Go ahead and include it, just as everything else, shader.h. So the name of this class is a bit misleading. It's not really a shader. It's a shader program. Because if you come look at our main file here, we have this uint vertex and uint fragment. So each of these is a shader. But if we scroll down, we have this uint program, and that's where we attach our shaders, and the shaders are linked, and that's the group of code that is actually run on the GPU. And there's not really, I can't think of any benefits that you could gain by having a class represent just a single shader. I suppose if you had a more complex pipeline and you were using more than just a vertex and a fragment shader, I could see the benefits. But for our purposes, we're just going to put both of these into a single class. So really, this shouldn't be called shader.h. It should be called shader program or something like that. But whatever. So this will be a GL object because the program has an ID. Okay, so let's do the private stuff first. All the member variables. So we're going to need once again, the goal of this class is to get our shader source code out of the main file and into an external file. So we're going to need some way to read that from a file and also to separate the contents of that file into a vertex shader and a fragment shader. Now you could do it, and it might even be better to do it, have one shader in each file, one file for vertex array and one file for a fragment shader and one file for a vertex shader. But for this project, I've decided to do it all in a single file, just because it'll reduce scrolling and flipping between files for you guys. I think it'll make it a bit easier to follow. But I think overall it is probably better to have each shader in a separate file. But for our purposes, we're just going to need one file path. So we're going to take in that one file path, open the file, assuming it exists, and we can throw some error if it doesn't exist, and then separate the contents of the file into two groups, the vertex group and the fragment group. And each of those groups can just be a string, just a single string. As long as it has those new line characters after it, it'll be exactly the same as what we've defined here in our main file, just a single string with new lines after each line. So to simplify things just a bit though, I'll create a private struct here called shader sources, and we'll store both the vertex source and the fragment source. And this is just a simplicity thing. It doesn't really serve a functional purpose. Okay, so then we have two important functions. The first is going to return one of these shader sources objects given a file path. So it's going to open a file, read the file, and return, split it into two strings and return it. And the second will take in a single string, so one of the strings from our shader source object, as well as the type of shader that's being compiled, so vertex or fragment, and it will return a uint, which is the like the OpenGL pointer, the ID of that shader. And then in our constructor, that's where we'll handle like the ID of the program that we bind both shaders to. So I guess that might be helpful actually, if I go ahead and outline the constructor. So we're taking in a file path, and then we can go ahead and assign to our ID variable that's part of the GL object base class. We'll just go ahead and create a program for that. And then of course we need to, in our destructor, do GL delete program on our ID. So let's sort of separate out the steps here. So we're going to parse, which is going to have a single call to parse, and then we'll have a vertex equals compile on something, fragment equals compile on something else, and then we will attach the vertex and the fragment shaders to our program, which is now stored in MID. Then we'll finalize the program, which does all the linking stuff and the validation, and then delete vertex and fragment. So those are the steps. So the first step here is to actually read the file and get the strings. So let's write that first, parse. So the way we do this is with an IF stream, an input file stream. And you just give it a string, which is the file path. Now, if this file path is invalid, like it doesn't exist, or the file is somehow protected, I'm not sure, you can check that with, oh, and I forgot to name this. I'll just call it in. You could call it input or file, whatever, but I like in. You can check whether or not it was successful with the isOpen method. And obviously, if it's not open, something went wrong, so we want to throw an error and just return. So say error opening shader file, and then we'll give the file path, which is FP. And then we do have to return a shader sources object here, even if there's an error. So I'll just go ahead and return one with 2 empty strings, just to sort of signify that something went wrong. Okay, so once we've verified that our file is correctly open, we can start reading it. So we're going to read our file line by line, and basically have 2 strings that we are constantly appending to, depending on whether or not we are reading a vertex shader or fragment shader. So we need a space to put the current line, and then we'll have this cool structure called a string stream, which is this yelling at me? Incomplete type is not allowed. Ah, okay, I forgot to include that. That should be in our pch.h up here. So I have iostream, fstream. Should also go ahead and add string stream, sstream. So this will just allow us to easily append to our strings and then return them at the end. And then another thing we need, and again, if you were using more than 2 types of shaders, you would want a sort of better system for this. But for our purposes, we can just use like a uint. We'll call it current type. And this is going to be the index of an index into this string stream array of the one we're currently changing. So like index 0 can be the vertex shader, and index 1 can be the fragment, like that. So we'll just start it at 0. It doesn't matter what we started at. And then, so we've got all the stuff set up. Now we actually read the file. So we can get the file one line at a time with this getLine function, and we pass it our input stream and line. So it'll read the line, the next line from this file, and store it in this variable here. And now we're going to add a bit of our own syntax onto this, just so that we can tell which type of shader we're currently in. So it's not going to be like a GLSL thing. It's going to be just for us, just for this class to figure it out. So we'll do if line.find hashtag type. So it'll be sort of like a compiler directive, like hashtag include. It'll be hashtag type. And unfortunately, this returns like an unsigned integer of the location of this substring in the string. It doesn't just return a Boolean. So we have to do if that doesn't equal standard string in pause, which means like this is just like to signify that it's like an invalid index in a string. So if the index of this hashtag type string within our line is not invalid, meaning that it does exist in this line, then we'll determine which type of shader we're in. So we'll do another line.find for vertex. And if the line contains vertex, then we'll set current type equal to 0. Then we'll do an else if, looking for fragment, trying to find fragment. And if we do find it, we'll set current type to 1. Otherwise, so if our hashtag type directive here is not vertex or fragment, then it's invalid. So we'll print an error, invalid shader type on line, whatever. And then once again return that sort of empty object just with 2 empty strings. And this is something that you should make sure you get right. So line is a standard string, but this %s token in printf expects a const char pointer, and those are not the same thing, obviously. But the way you get the char pointer of a string is with this c_string method. So that'll print it out correctly. If you don't do this, it'll still print something out, but it'll be just garbage, and that can be confusing. So make sure you have that .c string on there. Okay, so otherwise, if we don't have a hashtag type directive at all on this line, then we will take the current stream we're operating on, so streams at current type, 0 for vertex, 1 for fragment, and we'll just append the line to that stream. Now, this getLine function, it reads the whole line from the input file and stores it in line, but it chops off the new line at the end. So we're going to have to add that manually with just a single character /in there. And if you don't add that, it will mess it up. Okay, so this while getLine thing, getLine will eventually return false once you've reached the end of the file, so that'll run until you've read the whole thing. And then once you have, you should close the file. That might not be required, but I don't know. I'm sort of using it like a Java file where you're supposed to close it manually. And then once we've done that, we can return a proper shader sources object just by extracting the strings from our string stream. Wow. Like that. So we get the vertex stream and get the underlying string, then the fragment stream and get the underlying string. And that lines up perfectly with our definition up here because vertex is first and fragment is second. Okay, so now we have our the data from our file. So we can go ahead and write that part of the constructor. So we'll have some shader sources object here. I guess I'll call it source equals parse, and we'll just pass it the file path that the constructor takes in here. We'll call that sources just to make it match. Okay, so now that we have this, we need to send the vertex part of this object to the compile function and store it in a shader, and the fragment part to the compile function and store that in a separate shader. So let's go ahead and write that compile function now. So this is just going to wrap, it's going to do like this stuff, I guess. It's going to actually create a shader and then attach the string we give it, or set that string as the source, compile it, check for errors if there are any, and then just return it. So the first thing we'll do is just get an ID, which will be GL create shader. And this requires a type, either vertex shader or fragment shader. But because our compile function is going to be used to do both, we'll just take in that type as a variable and then pass it along right there. And then the GL shader source function is a bit weird in that you can see the third argument here is a pointer to a const pointer to const chars, which basically means it's a pointer to a string instead of just a string. And the way we've sort of taken in our source here is with a string object. So let's write this out here. The first thing is going to be ID. That's the shader we want to operate on. Count. I'm not sure what that is actually. I think that might just be the number of source strings. That's probably why this is an array. So I guess what that means is that you can either give it a single string that where each line is separated by a new line, or you could give it an array of strings where each line doesn't need a new line. It's just a different element in that array. I'm pretty sure that's what that is. But we just have a single string, make it easier on ourselves. So we need to get the const char pointer from our string, which, as you saw earlier, is done with cstring. And then length is going to be null pointer. We don't need that. But this is yelling at us here. It says argument of type const char is incompatible with const char pointer const pointer. So we need the address of this pointer. And unfortunately, when you do this, you can't just take the reference of, or sorry, I shouldn't say reference because that's like a different thing in C++. You can't just take the address of an address like in line like this. You actually have to store it. So we'll just do a simple sort of workaround here. Just store that pointer in a local variable and then give the address of that local variable, which is kind of annoying, but whatever. It's not that big a deal. Okay, so this sets the string we've given it as the shader source, which is good. And once we've done that, we can compile our shader. And we could be done here. We could just go, okay, I'm done, return ID. But it's best to check for errors, especially when we get into more complicated stuff. We should really use the error reporting system built into OpenGL because it's quite good. It's like very explicit. It gives you line numbers. It tells you more or less like what's going wrong. So yeah, we should make use of that for sure. So we need an int here, and what this will be used for is we're going to use this getShaderIV function, which just like gets information about a shader and stores it in a variable that you give it. So our shader ID is ID. The variable we want is the GL compile status, which will tell us whether or not there was a compiler error, and then we'll store the result of that in our result variable. So now, if our result is equal to GL false, which means it did not compile correctly, and these GL true and GL false macros are convertible to Boolean, so we could do if not result, which is the same thing, either way you want. So if there was some error, we'll print out an error message of our own, and then we'll give the OpenGL one. So we'll say shader compilation failed, boarding, and we can give like the type of our shader, just because we're using only two types, vertex and fragment. We can make this very simple by checking if the type that we've passed in, this GL enum type, if that's GL vertex shader, then we'll print out vertex. Otherwise, we'll print out fragment, because those are the only two types we're allowing. Okay, and then I like to also print out the source code. It's just a bit more convenient, so you can see right in the console what it is. You don't have to flip back between the error printed in the console and like the file in Visual Studio. So we'll just print the source, and then we'll actually get the error from OpenGL. So the error is a string, and in order to store that string, we need to know the length of it. So we'll have another variable here called length, and we'll use that GL get shader IV function once again on ID, of course, and the variable we want is GL info log length, and store that in length. And now that we know the length, we can create a character buffer to store it. Of course, this has to be dynamic, stored on the heap or the free store, because it is not a compile time constant. It happens at runtime. And whenever you create an array on the heap, you need to delete it once you're done. So we have our buffer now, so we can get the actual error with GL get shader info log on ID. The size of our buffer is length. The pointer to it is and length. Uh-oh, what happened? And then I've been having trouble with my keyboard lately. It's like really old, and sometimes it gets stuck like on caps lock. There we go. Okay, sorry. So we're giving the ID of our shader, the length of our buffer, a pointer to our buffer. Or no, that's not right. A pointer to our length. This we're not going to use. What this is though, and this looks really confusing because we're using the same variable. But this third variable here is the length of the returned string, which is weird because the way we're doing it, like we get the length beforehand and then create a buffer of exactly that length. But I suppose what you could do is just have a buffer like already allocated of like a size, big enough that it could store any reasonably sized string. And then this would return the length that was actually written to that buffer. But we're not doing it that way, so we'll just give it and length. We could also give it null pointer because we're not going to use it. That might be a bit clearer. And then pass it our actual buffer, like that. Okay, so now that we have the string, we can just print it. And then once we've printed it, delete it because we don't need any more. Now the last step of this cleanup is there was a compiler error, so we don't want to do anything else with this shader. So we're going to go ahead and call GL delete shader on our ID and then return 0. So this is a bit interesting. I was talking about last time in our unbind functions how I always use 0 for unbind because that's usually like an invalid index. I'm not sure if that's the case for shaders. It might be. I think it would be like better to return -1 here or something. But either way, like we've made it very clear that there was some error that happened. So like if the program fails at this point and this 0 causes something weird to happen, there's no worries because this is never going to be part of like normal execution. But yeah, okay, so we've checked our compiler errors. That's the only thing that can go wrong at this step. Once we attach them to our program, we might add some code to check like linker errors, which is very similar to this. But we don't have to do anything else in this step, so we'll just return our shader's ID. And now that we have this compile function written, we can actually create our shaders. So we'll have a uint vertex, which is equal to compile. The source is going to be sources.vertex, and the type is GL vertex shader. And then we'll have fragment, which is basically the same thing, like that. Okay, so where are we up to in terms of our main file? So we've given the sources, we've compiled our shaders. We have a program, so the next step is to attach our shaders to the program, finalize the program, and then delete those shaders. So we'll attach them here with GL attach shader. Our program is stored in MID, We'll attach both the vertex and the fragment ones. Then we will link our program. And validate program. I'm not actually sure what the validate part does. I know linking like resolves references between different shader stages, but I'm not sure what this is. But it's necessary. And then once both of our shaders are stored on our compiled program, we can delete the originals. Delete shader vertex and delete shader fragment. Okay, so now we're done. We are going to add more to this file today. And while we're here, actually, I should go ahead and delete the copy and move constructors. I forgot to do that at the start. So we are going to come back to this and add some more today, but this has all the functionality that we're currently using in our main file. So let's go ahead and start replacing all of this with our new object. So the first thing we're going to do is create an external file to store both of these and use that like hashtag type sort of syntax that we said to split it up into the vertex and fragment parts. So I'm going to create a new top level folder here with add, right click on the project name, add a new folder called res for resources. And we'll store our shaders in here, we'll store our images in here, just resources used by our program. So there is this like, if you look at like the templates for files over on this left side, there's this HLSL type, which is used for Direct 3D, which is DirectX, Microsoft's graphics API that only works on Windows. I don't know what that is, but there's not like a .glsl. It doesn't matter though. You can just come into the name here and specify it yourself. So I'll call this one just shader.glsl. And the file type doesn't matter at all because we're just reading it as text. So this could just as well be shader.txt, but I think it's nice to like give it a proper name. Okay, so now what I'm going to do is I'm going to move my main file over here.
I'm not sure how you create .glsl on Xcode.
You should be able to
never
just
mind.
do add file. Yeah, and Xcode actually is really nice in that it has built-in syntax highlighting for GLSL, which will help you a lot. Visual Studio does not. There is an extension you can install for it up here. If you search online for like GLSL, there is one, and this is another reason like why it's technically better, I think, to separate your vertex and fragment shaders into two files, because when you use that syntax highlighting on our file, which has our own sort of like hashtag type stuff in it, it won't recognize that and it'll yell at you. So I've just not installed it for now. I didn't use that as part of the setup, and it's not that big of a deal. So all I'm going to do is I move my main tab over to this other window here, and I'm just going to copy it. But of course, first we have to have type vertex. And then we have version 330 core. And you can copy this directly if you want. You can copy paste, but I'm going to rewrite it just to give you guys some time. Okay, that's our vertex shader done. I'll tab down a bit, do a fragment. Okay, so that's all of our shader code in a new file there. Now back in our main file, we can take this whole big ugly chunk of shader stuff, comment it out, and then create a GFX shader called shader, and our file path will be res/shader.glsl, like that. Oh, we forgot to, it won't let you create it. It says object of abstract class type shader is not allowed, blah, blah, blah. The reason is that we're inheriting from GL object here, and we haven't defined a bind and unbind, which is obviously very important if we're trying to actually use it. So we'll do bind here, and we can look down at our main loop to see what we're doing. We're just doing GL use program. And that's going to be imID. And then our unbind I'll set to 0. Again, that may cause problems, but you're never going to need to use it. Like, whenever you bind a new thing, it overwrites what's already there. So if you have two shaders that you're trying to swap between, you can just bind shader A and then bind shader B, and it'll do the same thing as if you bind shader A, unbind shader A, and then bind shader B. It's just that this can be helpful if you're debugging stuff, so I included it, even though all of this is already planned out, so we're not going to have to troubleshoot very much. But yeah, so now that we have a shader, we can go ahead and do shader.bind, and let's see if it works. Perfect. Get exactly the same output with a lot less code in our main file. So I'm going to go ahead and delete all that nonsense. I'll delete all these comments as well, don't need those. So now what we're going to do is sort of just condense this a tiny bit more by giving our renderer a shader. So our renderer will store a shader object. And once again, as I keep saying, like if you're doing something more complicated, you're probably going to be using multiple shaders for each frame, and so it might be better to just have your renderer like not store a shader, but instead take it in as a parameter to the draw function and then use that. But for our cases, we're doing everything with one shader, so we can go ahead and just create it here and save ourselves a bit of work. So we'll have a shader, imShader. And then of course, now that we have that, we need to create it with a constructor. So we'll just have that file path, pass it right on through to that constructor, and we don't need to do anything else. And then while we're here, might as well delete those unnecessary copy and move constructors. And we don't need a destructor either. There's nothing to clean up really. But now that we have a shader, we will also bind that in our draw function with imShader.bind. And this actually will not compile right now because of the order that I've included things in. So in my all.h here, you see I have shader underneath render. I'll just go ahead and compile to prove to you. imShader, unknown, missing type specifier, blah, blah, blah. But if I include shader above renderer, renderer will now have access to it, and it will do just fine. Okay, so now we don't need to create a shader, a standalone shader in our main file here. We can just pass the same file path to the renderer constructor. Go ahead and delete our shader there, and then we don't even need this shader.bind anymore because it'll be handled by renderer.draw. So run that, and exact same thing. It's just a bit more of a convenience for us, save us some typing. Okay, so that is like everything. I'll go ahead and move. Well, I don't know. I'll just expand this. That's all of the like OpenGL code that was in our main file is now in our own classes, which is great. So we've like achieved our initial goal, but we're not done. We're far from done. There's always more to do. And as I said, we're going to come back to the shader class and add some neat stuff there. So we're going to edit our shader code just a bit to include this new type of variable called a uniform. So uniforms are basically data that you send to the GPU from the CPU. It's much like you know, a vertex buffer, which has all your vertex data, or an index buffer. The difference is the way in which the shaders receive a uniform. So you see here in our vertex shader, we have this layout, blah, 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 blah. So this reads from the vertex buffer data, like the bound vertex buffer. But uniforms aren't bound to anything. They're just sort of like standalone, and you set them one by one. So you can declare a uniform with the uniform keyword. And then you give a type, and then you give a name. So let's say, just for sake of example, that we want to offset all of our vertices by some constant value. So we'll have a uniform float. I like to precede these names with u underscore. I'll call it u offset. And then in our GL position here, we will just do I position plus u offset. And this is basically what we're going to do with the camera, except that the camera is going to be a vec2. But for now, this will suffice. So by default, these uniform variables, technically, like their value may be undefined, but in everything I've ever done, they're like 0 initialized. So this u offset will be 0. So if we run this now, it'll give us the same thing. Now, I think this isn't like an example I should be showing, because once again, like it's probably technically undefined what the value of that is. But my point is that we have to set this ourselves. You can't give it a value in the shader. You have to set it from your CPU code. And the way you do that is a bit complicated, but luckily we have our new shader class that we can sort of wrap everything up in. But for now, I'm just going to sort of show you in ugly OpenGL code. And in order to test this, I am going to comment out this private bit right here in the renderer, just so that we can access our shader from our main class, because we do need the ID. So that's just a convenience thing for now. We'll come back and change that later. So we have this function GL_get_uniform location. And it takes in a program ID, which for us will be render.mShader.getID, and the name of the uniform you want. So the uniform we are looking for is u_offset. And this returns an integer, which is the sort of internal like index, I guess, of this uniform in the shader. It's nothing that you can really operate on. It's more just to pass to other OpenGL functions. So once we have this index, and there is like error checking you can do with this as well, but for now we'll just ignore that. So once we have our index, we can actually set the value. The way you do this is with these GL uniform functions, and you can see here it starts at GL uniform 1D, and you can just keep scrolling. There are so many of these, and you need to call the correct one in order to set like the right data type. So we're going to use some clever C++ tricks to like help us handling all of those different functions in our shader class, but for now, we're just setting a single float, so we can do GL uniform 1f. And you see here it takes in this int location, which is our index, and then the value you want to give, a float v0. So let's say we want to offset everything by 1, which, if you remember in OpenGL, the coordinate system is normalized from -1 to 1. So this should push part of our rectangle off the screen. And it didn't. Shoot. I'm actually not sure why that is. Oh, this is why. Our shader isn't bound. So if I go back to the render real quick, we can see we create the shader in the constructor, but we don't actually ever bind it till we draw. So I think that's the error here. So I'll just do, once again, this ugly temporary workaround, accessing the shader directly and just bind that like that. And there we go. We've offset our rectangle by 1, so in both axes, so half the screen in width and half the screen in height. And if I give -1 instead of 1, it'll give the opposite effect and move to the bottom left corner, just like that. And yeah, so a uniform is basically just data that you want your shaders to be able to access that are sort of standalone things. They aren't part of vertex data, they aren't part of index data. They're just single, like, smaller variables like this. Okay, so now that you know what a uniform is and like what they're used for, what they do, let's properly wrap all of this up in our shader class. So the very first thing I'm going to do is, just before I forget, come back to the render and uncomment that private, because that's pretty egregious. You should never, like, that's a terrible violation of object-oriented concepts. But yeah, anyway, so uncommented that, make that private again, and in our shader, we're going to do 2 functions here. Well, we're gonna have 2 private functions to handle, you know, common functionality for us, and then unfortunately we do still have to create, like I showed you how there's like GL uniform 1D, 1DV, 1F, 1F. So for all of these different ones that we want to use, we will still have to create a function that is, you know, a public function for our users to use, but we can abstract most of the functionality out into just 2 private functions, which will make it a lot easier to add those. And the first thing we're going to do, well, we'll have two private functions. First is set uniform, which will take in like the name of the uniform. It'll find the index of that uniform and then set it to whichever value you've given it. And then the second is going to be get uniform location, which will take in a string, the name. So this is going to be used by the set uniform function to get the actual index of it. Now, something cool about uniform, like the index of a uniform, is that it doesn't change during runtime. So in order to speed this up, we're actually going to cache the indices of all the uniforms we look up. So we'll use a standard unordered map. This is basically just a hash map if you're from Java. And we're going to map strings, so the name of our variables, to an int, which is the location of our variables. And we'll call that im_uniform cache. And we will use this in our get uniform location. So the first thing we'll do is check if our cache has an index for this string. So if the whatever variable we're setting, if we already know the index of that variable, we'll just return it. So we can do if im_uniform cache.contains our string. We will return. Actually, this is a slightly inefficient way to do it. Let's do it a bit better. So we can do this auto keyword. I'm not sure if I've used that before. But this is kind of a cool thing in C++. It makes the compiler figure out the type of this. because really it's going to be something like really obnoxious to write. It'll be like a standard pair of a standard string and an int, like as a reference, something like that. I'm not sure. Const, yeah, it's just like really long, and that's probably not. Yeah, see, like you can see here, the error here. It's just like, what am I looking at? That's such a ridiculously complicated type. I'm not going to type that out. So you make the compiler figure it out. So you just say auto. I use this very sparingly because I think it can be damaging to the readability of your code if you use it liberally, just because the reader won't know what the type of anything is. But in cases like this where it's very clear that, okay, I'm just getting this whatever value it is from the map, I'll just throw an auto on there to make it easier to write. Now we want to check this cached will actually be an iterator into our uniform cache, which is sort of a standard thing that all of the STL, the standard template library containers have. They have iterators, which are sort of like pointers into the containers, but with some extra functionality. But all we have to do is check that it doesn't equal mUniformCache.end. And .end is sort of like the null iterator. It means like something that is not contained in the collection. So if we don't have anything cached, or sorry, if we do have something cached, if our pointer or our iterator cached is not equal to the end iterator, meaning that it is contained within our map, then we will return cached second. So as I sort of explained, what this is it's a pair of a string and an int with some extra stuff thrown in there. And that makes sense because we're mapping strings to ints, so our map is just a collection of pairs of strings and ints. And the second value of this pair is going to be the int, which is what we want. If we were to do the first value, that's going to be a string, and it's going to say you can't convert a string to an int because we're returning int here. So we'll return cached dot second. Otherwise, we don't have it cached. We're going to have to find it ourselves. So int location equals GL get uniform location. Same as we did before with our ID. And remember to do this .cstring thing on our string here. So get the uniform with the name we've specified. If we can't find it, if it doesn't exist, location will be -1. And here we can print an error. So we'll just say uniform with this name not found. And then return -1 as the index. Otherwise, we have found it and we can store it in the cache. And then return the index. So one thing you could do here is only look for uniforms that don't exist once. And by that I mean also cache location if it's -1. But you can see here, if it's -1, we just print an error and then return immediately. So it's not actually cached. And this is just a preference thing I have because every time, like if you're trying to set a uniform variable every frame, like if you have a camera or something that changes every frame and you're setting that every frame, this will yell at you every frame. It'll be like really annoying in the console. It'll slow down your whole program. So it makes it really obvious that like something has gone wrong. Whereas if you cache this, it'll print this error one time, sure, but then the next time you look for this thing that doesn't exist, that you think exists, this auto cached function will just silently return -1. So I don't know. I prefer to have it yell at me constantly. I think it's just a bit more obvious because like setting uniforms that don't exist is not something that should be done. There's just no reason to do it. Okay, so that's all we have for our get uniform location, just a simple map as our cache here. Now we're going to do a bit of magic in our set uniform. And I don't think I can explain it piece by piece. I'm just going to write it and then explain the whole thing. So it's going to be a template function, some type name t, and then this weird thing, type name args. And it's going to take in a t, obviously the name of the uniform you're looking for, and this other weird args thing. And then in this function, we are first going to bind our shader, of course. and then we will call the given function with get uniform location of the name we've given, and this third weird args thing. Okay, I've got that. I'll come back to that in 1 second. What I'll do now, just to sort of demonstrate it, is I'll write the set uniform. I'll just do the one we already have. So we're setting a single float uniform. So set uniform 1f, and we need a name and a float f to set it to. All we have to do in here is set uniform, our private function, with GL uniform 1f, passing that function as a parameter, the name of our uniform, and then the value we want to set it to. So what's going on here? Well, I think I'll start in the set uniform 1f function and show you why I need to do some of this weird syntax. So obviously, as I've showed, we have set uniform 1f, and you can see that takes a location and a single float. We also have set uniform 2f, which takes a location and 2 floats, 3f, 4f, which take 3 and 4. So we need some way to, if we want to make this functionality common of calling these GL uniform whatever functions, we need to be able to pass as many parameters as a given function requires. So that's what this type name ... is. This means, this is called a parameter pack. And basically what it does is the compiler looks at the variables you've given it, like the stuff. So you have to give it this t thing, which I'll talk about in a minute. You have to give it a name, and then everything else that you give it afterwards, the compiler will look at that and sort of create a temporary type, which I've called args, and make that one element. And that's what this syntax here means. It's like a type of args so that the compiler can infer what that is. Taking it by reference, that's not needed. I just did it so we don't copy anything. ... to show that it is a parameter pack, and then here's the actual name of it that we're using. And then to sort of get the values out of that parameter pack, so say we're passing in 3 floats. Those 3 floats will be packed into one variable name called args. But GL uniform 3f explicitly takes 3 separate float variables. We can't give it like a weird float array of 3 variables. It won't work with that. So we need to expand that back out into the original 3 variables with this ... syntax. So this is a bit of compilery magic. I think it's very cool, and I encourage you to look into it. This is getting a bit into what's called template meta programming, which is like programming with the compiler, I guess, to make writing code easier for you. So that's pretty cool. Now, this t thing, that's the first argument here, t function. You can see we've passed the name of this function, GL uniform 1f. So if I just look at that, at what that is, you can see it's defined as void pfn GL uniform 1f proc. So pointer to a function called GL uniform 1f procedure. Okay, so that's fine. That's like a weird complicated name that OpenGL uses to store that pointer. But what if I look at 2f? What is that? Hopefully it'll tell me. Oh, it won't because I have that. So 2f is a pfn GL uniform 2f proc. So it's a different type. And what this means is if we're trying to generalize this set uniform functionality, we're going to have to pass in different types of function pointers. And what better way to do that than with a generic type t? So that's all that is t here is just a stand-in. It really doesn't matter to us. It's just to allow the compiler to say, okay, I see this function pointer you've given me, even if it's different types for different calls, that's fine. I'll just create a template specialization of this function set uniform and use it for you there. And then once we've received that fn, that function, whatever type it is, we call it with this syntax. Because one thing that is common to all of these functions, even though they have different parameter lists, is the location is always first, and then you have the list of values. So 2f is like that, 3f is like that, 1iv is like that. So yeah, that's all this is doing, is it's sort of a wrapper for this GL uniform 1f function with whatever we've called. And the reason this is good is because now I can do a set uniform 2f that takes in a string reference name, a float x, and a float y. This is like a vec2 in GLSL. And I just have to call GL or set uniform with GL uniform 2f, the name, x, and y, and that will all work the same. So even though it is sort of tedious that we have to create a new one of these public functions for every GL uniform star variable that we want to use, like this makes it a lot easier. It's just one line of code to write. And you could probably automate this even further with some clever usage of like macros, like get the compiler to do even more of it for you. But I don't know, that's a little complicated and I haven't messed around with it. So we'll just do it this way. It's clean and easy to read. But yeah, so that's how we're going to set uniforms. We'll do it through our shaders, because once again, the goal of this library is to make it so that the user doesn't have to write a single line of OpenGL code themselves. So if they want to set uniforms, they can do it all through these public functions. So now we can just use this instead of doing the GL get uniform stuff ourselves in main. I will actually come in here to my renderer class and have a get shader method that just returns a reference to the shader, just so I don't have to make this public. This is like the better object-oriented way to do this. So now in here, well, let's just see what we get if we run this, because we still have this uniform in our GLSL, but we're not assigning it a variable. So it's just going to give us like a rectangle in the middle of our screen, which is fine, but we want to offset it. So we can do render.getShader .set uniform 1f. The name of it is u_offset, and the value, I'll give it 1. And this should give us that same top right thing as before. Perfect. And just to show you how easy all of this becomes, I'll go ahead and make this a vec2. And now we can just use that set uniform 2f function that we defined, and I'll offset it by 1 in both, well, to make it different, I'll offset it 1 in x and 0 in y, just to prove that it's different. So this should be all the way to the right of the screen, but not in the top. Yeah, there we go. So yeah, that's like a lot of that might be all we're doing with the shader class, actually. I mean, we're going to have to come back at some point and add some more of these set uniform whatever functions, but all of this work is like a really good foundation. It makes it very easy to come back and modify this and add what we need. So yeah, let's see what's next. Oh, and I may not have explained this really. I also may have, I don't remember, but OpenGL, GLSL will like convert groups of a data type into these internal data types. So like iPosition here, if you see, we're just telling it that this is a group of 2 floats, but we don't receive it as like float iPosition X and another float iPosition Y. No, it just groups it into a vec2 for us. And the exact same thing is happening with this uniform, where before it was just a single float, so we could use set uniform 1f, but if it's a vec2, we don't have to do set uniform vec2 or anything. We just do 2f, and it'll send both of those floats and put them in this vec2 for us, which is nice. Okay, so I'm actually going to come back to, before we do the next step, which we'll still have time to get to, I'm going to come back to this renderer class and do something a bit weird that even if you've used C++, you probably have not seen before. So we have this getShader method, which returns a reference to our shader, which is good because we don't want to copy anything, but we do call set uniform 2f. Now, in our shader class here, this function is not const, because if we go down the chain here, we have set uniform 2f. This goes to set uniform, also not const. It calls bind, which is fine. Bind is const, but then it calls get uniform location, and get uniform location is not const because it directly modifies this variable here, im_uniform cache. It stores stuff in our map. Now, all of that means that our setUniform2f function can't be const, and because that's what we want to use in our main method, we can't return this shader by const reference. So if I do this, you can see the compiler will yell at me, saying that those don't line up. You're calling a non-const function on a const object. But we want to be as const correct as possible. And generally what that means is just putting const wherever there's room to put const, like use it as much as possible. And in this case, obviously, there's a conflict. So this is something interesting that if you have more questions about, which I'm sure I'm probably going to explain this very poorly, but that const correctness document that I linked, it has a whole section, at least one section about this, which is the logical versus the hardware state of an object. Hardware state meaning what the actual bits are, like whether or not those change. That's one way to think about const. Another way to think about const is from the outside user's perspective. Has this shader changed? Has this object changed? Like my abstract logical idea of what this object is, does calling this any given function change the state of that? And there are several ways to look at this. You could say, okay, so my shader is like this C++ object that I'm using, and the setUniform2f thing modifies this other like GLSL shader program that I don't really have access to, so I'm going to say that's a constant operation for my shader. And that's something you could do, and I think that's a valid argument. Another way you could look at it is saying, like, this shader object is a C++ object, but it directly represents this OpenGL shader code. So when I modify that code, it should count as modifying my object, and therefore these setUniform methods should not be const because they modify the logical state of it. And this is something that there's not a right answer to. Like you can't tell people how to think about your data types that you define. But what you can do is sort of help them, I guess, like guide them in the right way. So we could declare these set uniforms as const, saying the GLSL thing is separate, it's on the GPU, I don't care. But my particular interpretation of this class is that it is a direct, more or less copy or a handle to the code running on the GPU. And so calling these functions directly modifies that code, and so should count as modifying the logical state of this shader. So I'm going to leave these as non-const. But in my renderer, I don't think the shader should count as part of the logical state of the renderer. Because, once again, and I mentioned this while we were writing this, but in a more complex program, you wouldn't store the shader in the renderer. I've just done that for convenience here. And so, because of that, I should be able to return this reference. It's not going to be a const reference because remember, my shader methods are still non-const. So I have to be able to call them from a non-const reference. So I'm still returning a reference, but I want this getShader function to be const because whatever modifications the user makes to this shader reference that I return does not affect the logical state of my renderer. The shader being here is just sort of a weird thing. It's like there for convenience. So I should mark this as const. But obviously the compiler yells at you. It says, you can't do this. It's trying to convert. It sees that this is const. It says, okay, this can't be modified, so I'm going to try to convert this to a const reference. It can't, so it yells at you. The way around this, and use this very sparingly, is mutable. This keyword that, again, you've probably not seen. It's not very common. But what this means is the following variable is a member of this class, just as it would be if it were not marked as mutable. But in constant methods of this class, this variable does not have to remain constant, meaning the value of this variable can change. So a clearer way to show this might be, just for the sake of example, if I have an int I here, and in this const method, I want to increment I. Obviously, that's going to yell at me because it says it must be a modifiable L value. This const here effectively means that I becomes const inside of this function. But if I mark it as mutable, I can do whatever I want with I. So I'm going to do that here. And again, this is something that's like up to interpretation, but this is how I like to think about it. So our renderer here has effectively not changed. Like, all we've done is make it so that you can call this when it's const. We're not even using a const renderer, but just to prove that it works, we could do that here. And that if this were not marked const, you would see it would say, you can't call that because this is a const object. You have to only call const functions. So that's the mutable keyword. It's very confusing, and unfortunately, it's more of an art than a science, which is not great when you're programming. But there you go. I just thought I'd introduce that to you at least. Okay, so real quick before we go, I'm going to take this vec2 u offset. I'm just going to rename that u camera. That's what we're going to use it as for right now. And what we're going to do is, we don't have like input stuff working yet. We can't get keyboard state or mouse state or anything like that. So we can't really have a camera that you can control. But what we can do is have it be controlled just automatically. So we'll have some like vec2. Let's make a math vec2 of floats called camera. And I'll set it to 0, 0 initially. Now we also want some other value called increment. And for right now, I'm going to set this very, very low. I'll explain that in a minute when we run it. So then in our game loop here, before we draw everything, we're going to go ahead and update this sort of camera vector and then send it to our shader. So we'll do, I think I'm going to have this like bounce back and forth just so you don't have to keep rerunning the program. So I'll do like if, and actually, yeah, I'm not going to do a vec2 yet. That's a bit too complicated. Even though we're sending a vec2 to the GPU, let's just have a single value called offset, and I'll initialize that to 0. This will just simplify it a bit because we only have like 5 minutes. So if the value of our offset is greater than or equal to 1, then we will reverse the direction that it's moving just by multiplying the increment added to it by -1. And then every frame, we're just going to add that increment to our value. And then we will send, oh, sorry, not value, offset. Add that increment to our offset. And then we'll send it to our GLSL with render.getShader.setUniform to F. It's called uCamera now. And then we'll just send the same offset for both X and Y. And then, you know, we're drawing everything here with render.draw. So let's run this and see what we get. Okay, so we have this thing bouncing between, you know, the bottom left and the top right. There should be 2 things that you notice here. Well, 3 maybe. One is that it sort of bounces back when the middle of this rectangle hits the corner, which makes sense because the middle of our rectangle starts at 0, 0 and then goes to +1 in either direction. So 0 + 1 ends up at 1, 1, which is, you know, the top right of the screen, and in the other direction it ends up at -1, -1, which is the bottom right or bottom left. So that's why it's taking this pattern. The second thing you should notice is that it's very jittery. It like slows down randomly and then it'll speed up. And the third thing you'll notice is that it might be barely moving on your system. I have a very fast GPU, And so this increment I've given here of 0.0005 still gives it like a decent movement speed. But the issue here, and this is the same reason it's sort of slowing down randomly and stuttering, is that we're adding a constant value to our offset every frame, regardless of how long it's taking that frame to process. Because not every frame is going to happen in the same amount of time. Computers have to do a lot of stuff. So sometimes, some process might interrupt Windows as it's processing your frame, and it'll have to do that for, a couple milliseconds before coming back to yours, and that'll cause a slowdown. And we'll fix this next time. We'll add some new stuff into our renderer that keeps track of time. And we'll use this value called the frame delta, which is the difference in milliseconds between the current frame, the start of the current frame, and the start of the last frame. And we can multiply that by our increment here to update the position in a frame time independent manner. So regardless of the speed your program is running at, the actual physical real world distance that the object moves, the time will be constant as it's doing this zigzag motion, regardless of how fast your system runs. But if you're not seeing it, you can divide this by 10 or 100 or whatever, and run again. But mine, that'll just be it hurts your eyes. So yeah, that just shows you, that was just a pretty stupid, dumb example to show you that basically how we're going to do a camera. I mean, obviously it's not going to use this weird sort of system, but we will just have a Vec2, and we'll update that with keyboard controls to have our camera sort of pan around the screen and move the relative position of the object. And that's something I guess I should point out, is that our object is not moving at all. On the screen it's moving, but its position relative to the camera is moving because the camera itself is moving. Our vertex data, it remains the same. All these numbers are the same. We're not updating at all. All we're doing is adding this U camera offset to that vertex data. So that's what's happening here. And if you've done any sort of graphics programming before, or really just looked into game design at all, you've probably heard this statement, which I think is awful. I think it's a really confusing misnomer, or maybe not misnomer, but it's just a confusing way to explain it, which people say in computer graphics, the camera, the world moves around the camera. I think that's really weird. I don't know why people say that, because it seems to imply that no actual object movement happens, which is just blatantly false. In this case, that is true. Our object is not moving. We're not modifying vertex data, but we will get it to a point where we want to have a player moving around the screen, and we're going to be directly modifying their vertex data. So I just want to sort of clear that up. If you've heard that before, the world moves around the camera. That's weird. Both things happen. The parts of the world move themselves, and the camera obviously moves, and that can apply offsets to the whole world. And I think what's confusing, or why that statement exists, is that you can see in our vertex shader here, that's basically what's happening. Because our vertex data won't be modified during the vertex shader running. Our vertex data will be modified during the same frame, but before we even get to the point where we're drawing stuff. And so I think that's what they're talking about, is within GLSL, for any given frame, all vertex data is constant. And so you just apply this camera offset. And so in that way, I can see how the world moves around the camera, sure. But I think that's a very narrow way to look at graphics programming, is only looking at the shaders, because there's a ton more going on. But anyways, I don't know. That may have been a useless tangent, but that's something that confused me for the longest time until I eventually just realized that, oh, hey, that's just a terrible description. So yeah, that's all we have for this time. Next time, as I said, we will modify our shader just a bit more. Maybe actually, this might be it for now. Eventually we'll come back and do input, and we can actually have a camera that we move around the screen with the arrow keys or WASD, whatever. But next time we are going to do textures. So we're going to create a texture class and like take some image on our system that we'll put in our resources folder and map it onto this rectangle instead of this ugly, weird, like OpenGL, like automatic interpolation stuff between colors. We're actually going to use an image that we create in Paint or whatever you use on Mac. So yeah, you have that to look forward to. Obviously, that's a huge step for any game. It's like you need to be able to display user-created graphics. So we'll create that. We'll add some stuff to our renderer to support it. And then that might be all we have time for, because that's going to take quite a bit of shader modification as well. So yeah, hopefully you're looking forward to that. I hope this was interesting. I hope it's getting more interesting now, because I think I've noticed, like based on the YouTube views, that a bunch of people watched the first video and probably got bored, and then so like I don't know, a third of the people watched the second video, which is unfortunate because we were doing basic like C++ stuff, just setting up a math library. It was very boring. But hopefully now it's getting more interesting for you, and for the people who haven't stuck around, I guess it's their loss. But yeah, thanks for coming, and I will see you this Wednesday at 4.